I've conveniently already opened up these keyboards. So I'm going to start with this one. This is a very interesting keyboard in that I was looking for this keyboard for a good 3 years, and I bid more for this keyboard on eBay than I've bid for any other keyboard.
How much did you bid?
Not telling.
How many digits in US dollars?
Not telling.
Okay.
I didn't have to actually pay that much because BAA, if you know who, I have an eBay arch nemesis, and So anyways, I beat him over this one. So what's interesting about this is the first generation of Fujitsu leaf spring, and if you pull out the cap, it's very unique. Do not touch this. Those little metal things are like the razors. Every time I clean this keyboard, I find myself having bloody fingers, and I don't know why. I don't feel it. Basically, I make it messy again. But it's amazing keycaps. So there's a few members on the forums that wanted me to convert this keyboard. So I said, okay, figure it out. Step 1. Lots of pins. So there are approximately, let's see my notebook. There's 16 pins in this thing. So right from the previous presentation, it's basically going to be parallel. Unless you have a lot of ground pins, it's going to be more parallel. So what I did was I figured out, I took a look at all the data sheets for a bunch of these microchips, and then I mapped out, I drew out from here, what all the pins were. So I figured out what physical earth was, what ground was, and what potentially were the data and output and input pins. So once I figured all that out, I soldered on some wires. Normally I would just take a connector, but this connector is super hard to find, and I only got them last week from a random surplus place that took forever. So they're just soldered on the back. So I would call this non-destructive because I just solder them off. It's very easy to take them off. So now I have my power and my ground. So I'm just connected to a breadboard. You can connect them directly to power. So I'm going to plug them into my ground. So now I'll explain what I have sort of lined up. So this is a power supply, variable power supply. I could have used USB. USB is 5 volts. But the main reason I don't want to do that is that I was talking about earlier that if I screw up my power and ground, it'll push a lot of current through. And what this can do is it can limit the current. There's multiple supplies, but this one has 2 knobs: a current limiting, which I'm going to turn all the way down, and a voltage level. So it can go to 0 to 24 volts or 0 to 500 milliamps. 500 milliamps is the limit of the USB spec. This one can do up to 4 amps. This is the one you don't want to start with. So basically what I'm going to do is I'm going to turn it on. So I'll turn it on. It's at 0, but sort of 0. So I don't trust the gauges on here. So this is why I have this cable, this BNC cable, which is a very fancy cable used for electronics. It's basically like cable TV kind of cable, but it has power and ground cables, and it makes it really easy to disconnect and connect things. So now that I've plugged it in, I'm going to slowly turn it on. So as I turn it on, notice this red light here is on. Might be hard to see. This red light on. This red light means that there's current limiting going on. So I turn the current to 0. So if I turn this back up, notice that it's starting to go up. So now I'm at 3 volts. 3 volts isn't high enough. It's 5 volts. So I'm going to bring it all the way up to 5 volts. Oh, turn the game on again. Get more current. It's an old keyboard. Takes a lot of power. Alright, so 5 volts. Alright. So all you need is approximately 5 volts. You never have exact voltages. If you ever measure your USB on your computer, it is probably not 5 volts. Sometimes on a laptop it would be as low as like 4.1. It's really awful. Some things will not work at that voltages. So now the keyboard is maybe on. So like I mentioned before, you don't know. However, you can test it, see if there's a key with an LED here. So if I press it, it turned on. So this is a really good indication that we were successful. If you don't have such a key, then well, you gotta go further. So we're already in good position, meaning we were successful in powering on the keyboard.
Could you use the caps lock key for modern keyboards to test out to see if it's coming through?
No,
Okay.
because the reason you can't do that is that LED state in the USB spec is handled by the OS, and the OS will tell the keyboard when to turn the LED on. So it's a completely separate mechanism. It has nothing to do with the keyboard itself. So if you let's see if it does this. Oh, look at this current limiting. Turn the LED on. This is how old the LED is. It requires more current when there's LED. The voltage will go down and all that kind of thing. Okay, so you now have a keyboard that probably works. So the next step is I have all these lines out. I have how many bits? 1, 2, 3, 4, 5, 6, 7. About 9 different cables. And most of them are likely data bits because I have parallel information. I need to be able to encode what I'm typing on this. So what I found earlier is there's 7 data bits that I defined. So it will change each one as I probe it. So if I just do this, let's see, pull this out without no pull resistor first. It's a little hard to see in this one, but right now I have it at, so if I put this, wrong probe. Okay, so right here, this is 5 volts. So I can define where my high voltage is. Now if I go here, this is 0 because it basically it's connected to nothing. And this cable right here is doing some nice isolation for me. I'm actually mapping ground to my relative ground, so I don't have to worry about connecting this little side cable on, because I have to, when you measure voltage on an oscilloscope, you have to relate your voltage to something. Otherwise you're floating like the pull-up resistor thing. So if I connect to here, it's ground, which is fine. But okay, so if you look really carefully, you can sort of see it sort of doing something, but it's just sort of wiggling. 5 volts is up here. It's literally doing nothing for you. This is a good indication that it's trying to do something, but it doesn't have a pull-up resistor. It's expecting to pull down the voltage whenever it changes. So if I attach this to a pull-up resistor right here, so I have all of these diodes right here going to 5 volts. So if I connect right here, changed. Let's try to make it change again. Oh, it changed there. So this is sort of disheartening in terms of what I'm doing. If I find 2 that change, so here's this one. Here's this one. So 7 and 8. So it's holding both and 4. So if I press 7, press 8, nothing happens. That's a little bit disheartening because there's even if other bits were doing something, I still don't know the change in state. So if I go to another pin, what's this one? This pin is an interesting pin. This is a clock pin. So remember how I was telling you you need to know when you're changing? This is that pin. So every time you press, this pin will go, whenever you press it holding down, it will go down. When it holds up, it will go back up. There's a delay on here because of the triggerings on the oscilloscope. But this is how you figure out I'm now pressing something or I'm now not pressing something. If you press another key, it doesn't really do anything. sort of tries, but definitely. So already it's sort of, it's not really worth it. Where I know there's data bits. I can probe further. So what I can do, I don't really want to. I can attach all of these wires to mask register. So I'm going to attach my logic analyzer. So the first pin you do is you ground. So it's the same thing as this reference here. Attached to a ground pin. Then I'm just going to choose more or less random pins to each of the sides. This one more. Logic analyzers are great things. You really do need one. Oscilloscope is not good enough really to do with this kind of stuff. Oscilloscope will tell you when things change, but it's very hard to record data about time on an oscilloscope. Fancy ones can do it, but you've got to pay a lot of money.
What logic analyzer are you using?
I'm using Salier, or whatever. They're out of San Francisco. They make a nice. It's expensive compared to the cheap ones, but if you fry it, they will replace it for free.
Oh wow!
I have actually fried one. It is really hard to.
Is it a card on your
No, it's right here.
PC?
It's a USB little thing. Yeah,
That's it?
That's it. And then you have some software, Windows, Linux, Mac, which is great. So I highly recommend this stuff. You can get cheaper ones that very easily that will do the same job. But
The only one I ever use is about the size of my Miata. So
yeah,
that's blowing my mind.
yeah, exactly. Yeah, you know.
If you're a terrible person, you can get like clones of that off of
Yeah, probably.
like Alibaba for
Yeah.
$5 or something.
Deal Extreme sources.
Deal Extreme, you can get really cheap ones.
How much are these?
So this one's like, I'd say like 120-ish. But considering it, you can fry it, they'll get it for free, and they have really good software. The software is actually really good. Like, so what? Salia. But yeah, they're out of San Francisco. So they've been around for a while. They even have their own like logic. They have a like digital oscilloscope they're trying to do too. But yeah. So I have now attached a bunch of pins. So what I'm going to do, find a keyboard. So let's see. So the first part of it is that I have to say how many samples I want. So I'm going to say, just so I can be lazy, 10 million samples and at a certain speed. So 10 million samples at 24 megahertz isn't all that many samples, but you also have to keep in mind your USB bus has to be able to keep up. I find for keyboards don't run closer to like here, so you can be generous. Even like modern things like I2C or UARTs or serial buses, they don't run that fast. So you can easily do like, I don't know, 12 or 8 or something.
That's gonna be less than a second though, right?
Yeah, well, you'll see it. So what you can do with here is you can set triggers and like only start when something changes. So I'm just gonna start it and I'll show you what happens. But so see, that was less than a second right there. So if I go 50 million.
Could I get you two to step back?
Oh, sorry.
So let's start. Yes. So it's going to show here, and then show a change. There's not a change.
Now these signals are clean because they're digital, right? This is
Yes,
not the
this is
actual
digital.
voltages.
These are not actual voltages. These are that's the big difference between a logic analyzer and an oscilloscope. Oscilloscope, you're measuring the voltages. A logic analyzer is your logic, 0 and 1. And that's why it can be so small compared to like this oscilloscope. But you're trying to get different information. Now, what's neat about this software is it has these little analyzers. Let's see.
Really?
So you go simple parallel. And let's see. I think channel 7 is the clock. Probably.
Yeah.
That, wow. How's that on?
How did you know it was falling edge?
It's not really falling edge actually. It's when it is. This analyzer, it should tell like when. Yeah, that is a neat question. But falling edge and rising edge is when the edge is going down and going up.
Yeah.
But basically, you just have to sort of look at the protocol. It's like, when do you want to read the signal? So basically, what we want to read the signal is when it changes down. Right? So, but technically, on this keyboard, I wouldn't trust it. When it goes down, the signal probably hasn't propagated yet. So if you're reading too fast, if you're reading slowly, it doesn't matter. Like, you just care if it's 0 or 1. But if you're reading quickly on a modern microcontroller, that is something you do have to worry about. So here's what it's done for me. So if you look at the bottom here, I, K, K, A, bracket, I, Q. And so if I go over here, it's doing ASCII for me. So I can do ASCII and hex. So now if I go into here, it's reading all these lines, these different positions, and it's determining what it is. Now, this might be right, but at some point it doesn't matter. You just have to sort of massage it to the right way and say, this is what I care about. So yeah, that's one of the ways the logic analyzer works for parallel. So you just record all the lines at that instance in time. That is your bit, or that is your byte. In this case. But,
What
yeah.
do those clocks normally run at on the keyboards?
Anything.
Is it
Anything. I had a keyboard once where you supplied the external clock. I could probably clock it at like 30 megahertz.
Yeah.
I'm sure I would have ran into electrical engineering problems.
Yeah,
But I could run it because there was actually no microcontroller on the keyboard. You actually supplied the clock for the keyboard to actually do a shift register to shift each of the keys. It was a noisy nightmare, but it worked pretty good.
They're all different. Huh?
Yeah, they're all different. That's what sort of makes this interesting. As soon as they got to AT, XT, PS2, and they all just sort of standardized. So a lot of this is for the custom application where you get a computer that didn't deal with that, or before that existed, or they didn't pay in their money to join the spec, or those sort of things. So yeah, I'd say that's about it for this keyboard, because I'm basically saying I give up on this keyboard. It's cool. It really needs a
progress, man. With that logic analyzer, I think.
So I already sort of knew that it's one key rollover. So you could make a keyboard. You could make this USB, but it's not a useful keyboard. That is basically why I say give up. It's just basically a fun puzzle at this point. But yeah, I mean, I've done keyboards. You should usually always turn your power off. We're 5 volts here, so it's pretty safe. I can basically touch everything, and it will not hurt me. But if you touch things together, you can hurt other things on the board. So that's more of the reason. It's safety of your work. There's the other rule of thumb, like when you're engineering something, buy 2 of everything, always, no exception. And you're always going to blow up the part you didn't buy 2 of at the worst possible time.
Well, you also have to run both when you get them, because half the time they don't do the same thing.
Also very important. Tolerances and all that kind of thing, like resistors, like 1%, 10%. For pull-ups it doesn't matter, but for certain other things they do matter.
This is that kit multimeter vintage.
Yes.
Amazing.
I saw it halted and it didn't have a power cable. I was like, that's mine. And it actually came calibrated reasonably well. So I didn't even have I have the data sheet for it to do the calibration, but it's like to really calibrate something you need some like good piece of. This is an endoscopy keyboard. So it was used for a basically what's called a keyboard condom. You know those things, the plastic cover. So that's why it looks so clean. It's because it always had this cover on it.
Did you put that keyboard inside somebody?
I don't know.
They're bad.
No, they're bad. But it's nice clicky. It's mostly linear, but it is a nice clicky switch. Yeah. So somebody on the forums recently said, "Oh, I got one of these," and so I said, "Hey, I'll use that for the demo." Yeah. So this one's a little bit simpler. Well, it's about the same. It has an easy connector. I got this for free, like I mentioned before. So basically, you look at this is called a DIN connector. It's very common in keyboards. There's a lot of different kinds of DIN connectors. Epson is very famous for using an obsolete version of it that looks like a horseshoe. I managed to get some, but I don't know how you get them anymore. And basically, they will not fit any other version of them. But this is a standard one. This is the one that would work on a terminal model F, like 122. It's the same connector. That's why I have one of these. And it fits nicely into a breadboard. So the only annoying part is that there's 2 pins vertical to each other, so the middle pin is next to another pin, so it doesn't breadboard nicely. But fortunately for me, the middle pin is not connected, and so it's like totally perfect. So I can just plug it in. So yeah, I basically just plug it in. I figured out what VCC and ground are. There's a few. If I go to my next one. So when I do the pinouts, I usually do pinouts for this part, pinouts from the connector side, pinouts from the opposing connector side, just so when you're actually cabling up, you can say like, I think this goes to here, it goes to there, because you have to think about all the pins and how they connected. Because you don't want to screw up that VCC and ground thing. I've screwed up a few times, and I'm really thankful I had a current limiting power supply. So I shall now turn it on. Yeah, it's 5 volts. I didn't limit it, because I'm bad, but it's not using that much. So it's now on. Let's see. Sometimes you can see voltage drops. You press those keys. No, not this one. Yeah, some keyboards do. You can see the voltage really drop when it has to actually do something. So it's now on. I've already added the pull-up resistors in this one. So if I measure this one, go here. So if I press signal. This scope is nice because it auto calibrates a lot. Right, that's the Raggle stuff. I have an analog scope, so I have to like tweak it all the time. So this sort of just does sort of an okay thing, not an ideal thing, but it'll give me something that I can read. But basically, it's giving me something, and it looks like a serial thing. So this is good. Now if I go to the other pin. It's just giving me this pulse. So that indicates to me, I'm not as familiar with this scope. I'm not sure if I can do it on the fly, but if I map the 2 lines beside each other, one will be a clock and one will be the data. So the reason why it's only looking like this is because it's just constantly doing that. It's just hold it like this.
Now, can you get the scope to trigger on the
Yes.
keyboard clock in order to?
Yeah, I'm not familiar with the scope, so I don't want to
Yeah.
I'd be fiddling around with that for a while. But once you're familiar with your scope, you can get it to trigger and show you. So you can do like basic things like a logic analyzer could do once you're doing the triggering and all that kind of stuff. Like analog scope, that's very important because it doesn't have this sort of delay thing. Yeah, but yeah, clocks are very nice for that. Okay, so now that we have something, Logic analyzer. Again, ground cable. I think it said in the help instructions that you should never connect the probes when your USB is not connected. There's a chance where you could fry, because if there was active voltage, it would.
Because they had the logic analyzer has nowhere to ground to? Or?
Basically, the path of least resistance could be through the chip itself.
Yeah.
And when it's powered, it can deal with that. But when it's not powered, it doesn't have the necessarily the means to do that. So that's usually you're fine. If you're dealing with keyboards, you're fine. I was dealing with an electric car with like 200 volts, and that's how I fried it. And I used the wrong ground, and it worked. It just because it definitely logic 1 and 0 at 200 volts. But yeah. So back to the software. I have to get away. So I'm using brown and black.
Thanks.
So this software has a really nice thing where if I don't need all the pins, I can hide all below me. So really nice. But the software was so good. So I'm going to remove this analyzer. And I'm just going to record something, but I can also set triggers on things. Like I could set a trigger on the clock itself, and that's when it was actually start recording. So if I went here, just press something. So let's zoom in. You notice at the top it has your time based, how fast. But here's my clock. So we figured out what this clock actually is. It's not a clock per bit. It's a clock saying I'm doing something clock, which is a useful. It's an interrupt for the computer saying stop what you're doing, process the keyboard. Yeah, and you can take advantage of this in your controller, so you can do other things while you're not doing this. If I had an analyzer, say async serial. So async serial means that there's no external clock for the bits. So I'm going to use D0. I'm going to use sensing audible. It doesn't work the greatest all the time, but okay. So now it gets sort of complicated. So usually you're okay to leave these as consoles, but yeah, you gotta set it up. So it's like, okay, how many bits do we got? 1, 2, 3, 4, 5, 6, 7, 8 ish. There's probably a parity because there's a stop bit. You have 1, 1.5. I don't even know what that is. Usually it's 1. The standard is usually is pretty straightforward. Parity or not. Basically, if you screw this up, it'll just tell you bad parity, and you can just flip it and see if it's good again. Least significant bit, most significant bit, or matter. For our cases, we can just flip them. Non-inverted, I believe, it's basically what 0 means and what 1 means. 0 could be high, or 0 could be low. So yeah, just special. I don't work with that. So this name. Oops, framing error. So this one thought it was 0x25 or percent. 1, 2, 3, 4, 5, 6, 8. Yes. Basically, what happened here is this start bit. Probably a parity. What's the baud that it found? Usually says 200. Yeah, it basically did an algorithm to figure out what the baud was, but I don't think we got the protocol just right. So we have there's a start bit. probably used to go a little bit faster. Let's put a we need to increase the baud rate.
So when you're doing early debugging like this, do you really match random keys, or do you focus on start?
So like
focusing
the
on
very
it?
first one I do, I just smash random keys, and then I will eventually focus on what is a U, and then what is a depressive U. So if I go, this is a really nice thing. I can build it. Yes, and just go to the previous one. So there's 25, 96. So these two here look very similar. So if you look at this one and look at the next one, they look very similar. They're like likely only 1 or 2 bits different. So it's likely that was the press and the release. So there's a different signal for press and release. So what you figure out, so this says 0, A5, but 2.5. So there's a little bit of difference. So and this
choose complement, but for
basically, so what another thing I can look at is that okay, I'll flip the meaning of the bits. Is it 0 for 1 or 1 for 0? And that usually cleans up the numbers a little bit. And then I figure out what bit does what. And then it just becomes basically a math problem where you just sort of figure like, okay, this goes to this. You figure out what the press and release are and try to find a rule for the whole thing. And that's your number. That's basically it. Software's pretty neat though. You can see how it takes 0.84 milliseconds for this period. All these nice useful things that you can use to when you actually make the filter.
is each dot when it actually probed it?
Yes, so that's what that means. Each dot is like where it found it. So if I change the baud rate here, like I think it's actually closer to like a let's go.
Framing and parody.
Yeah.
Ooh, good stuff.
Yeah, it's. If I'd actually done this beforehand, I would just use the perfect one. But it's basically fiddling with the knobs at this point and figuring out. This is the next most time-consuming part. It's like actually figuring out what it's doing. But when you're doing any sort of probing of protocols like I2C, UARTs, it's all sort of the same as this. Except then you sort of know what the speeds are. And you can adjust your knobs what they expect them to be, and then you can read the protocol, make sure it's doing the right thing. In this case, you're just expecting the keyboard's doing the right thing. You hope it is, and then you just go with that. That's it.
Nice.
That's cool. This tool.